Okay, series. A sequence is different from a series. A sequence is an ordered list. And a series is a sum. It's a sum of that list, basically. So if we add up all the terms of a sequence, we get what we call an infinite series or a series. So if you hear someone refer to a series, they are referring to an infinite series. The notation for a series is the sum from n is 1 to infinity of a sub n, which means a sub 1 plus a sub 2 plus a sub 3 plus a sub n plus forever. Or they may not put these n is 1 to infinity on there. They may just say the sum from of a sub n. It means the same thing, an infinite series. There's something called a partial sum, where we don't add up an infinite amount of terms, we just add up a finite amount of terms. So we could sum from 1 to n, the first n terms, and that's called a partial sum. So for instance, let's find the partial sum s sub 5 of n squared. So that means the s sub 1 would simply be where we add up one thing, and that's we let n be 1, that's 1 squared or 1. So s sub 2 would be where we add 1 plus when n is 2, n squared is, 2 squared is 4, so s sub 2 would be 5. So s sub 3 would be 5, the sum of the previous terms, plus when we let n be 3, 3 squared is 9, so that's going to be 14. S sub 4 would be 14, plus 4 squared is 16, so that's going to be 30. S sub 5 would be 30, the sum of the previous terms plus the fifth term, 5 squared is 25. So this is 55. So S sub 5 would be 55. You could make a sequence of partial sums. The sequence, S sub 5, would be S sub 1, S sub 2, S sub 3, S sub 4, S sub 5, or in this case, 1, 5, 14, 30, 55. You could consider the infinite sequence of partial sums. So the difference in this and this is that this is finite. So for an infinite sequence, it would be S1, S2, S3, S4. It's a list. It's not a sum. It's a sequence. It's a list of sums is what it is. All the way up to S sub n and forever. Okay, it keeps going. And so if you consider a sequence, because we just studied those, if you can find a limit to the sequence, then we know that that sequence converges. So likewise, if we take the limit as n goes to infinity of partial sums, S sub n, if we can find that it equals to some value, that it exists and it's a real number, then we say that that sequence, S sub n, is convergent, and that the series, in turn, the sum of A sub n, which is what this is made up of, is convergent. And so we write that the series A sub n is equal to S when it's convergent to the number S. The number S is called the sum of the series. If the sequence of partial sums is divergent, then we say the series is divergent. So let's look at this. Let's just see what's happening here. So for this first example, the second example, it says calculate the first 8 terms of the sequence of partial sums to 4 decimal places. So remember, partial sums is when we're adding them up as we go. So here's A sub 1, A sub 2. First, let's look at just the terms. A sub 3, A sub 4, A sub 5, A sub 6, A sub 7, A sub 8. Let's just look at the first 8 terms. Okay, this would be 1 over 1 to the 4th, which is 1. This is 1 over 2 to the 4th, 1 over 3 to the 4th, 1 over 4 to the 4th, 1 over 5 to the 4th, 1 over 6 to the 4th, 1 over 7 to the 4th, 1 over 8 to the 4th. But the partial sums would be when we add, this is A sub 1, this is A sub 1 plus A sub 2 S sub 2. S sub 3 would be A sub 1 plus A sub 2 plus A sub 3, and so on like that. So I've already calculated these, so I'll show you what I keep putting A. It's S. S sub 5, S6, S7, S8. So we're adding up all the terms, right? So A sub 1 is just 1. And then A sub 2 is 1 plus 1 over 2 to the 4th, which ends up being 1.0625. And then if we add the next term, it's 1.0748, 4645, 4568. If we add the next term, it is 1.139, no, 1.11390818. S sub 5 is 1.1155018. S sub 6 is 1.1166927. S sub 7 is 1.116696, 1.11669627. Uh-oh, did I write the same? S sub 6 must be 1 point, sorry. This one is, S sub 6 is 1.116, 27978. 27978. And then S sub 8 is 1.11694041. So if we start listing these partial sums, it looks like they're heading to a number. It does look like it might be going to converge, maybe to about 1.12 eventually. Maybe it, so it appears to converge, right? But that's all we can say is it appears to converge. We don't have anything really solid to tell us whether it's converging to that or not. So what we're going to be looking at is a few ways that we can tell whether a series is convergent or divergent. So let's look at the next example, or the next thing, which is a geometric series, which hopefully you saw some of this in pre-calculus, but if you didn't, this is what a geometric series is. It's a series where the next term in the sum, the next sum, is the next thing you're going to add is formed by just multiplying by a certain ratio called r, a common ratio. So the first term would be a times r to the 0. The second one is a times r to the 1, a times r to the 2, a times r to the 3. So if you see what's happening is you're just multiplying by r to form the next thing you're going to add. That's called a geometric series, and r is what is called the common ratio. So it can be shown that if you have a geometric series, if the common ratio r, if its absolute value is less than 1, then it will converge, and it will, you can find its sum will be equal to this right here, but this is a nicer way to write it. A sub 1 over 1 minus r. In pre-calc, we used to write this as s sub infinity. The sum of infinite amount of terms is a sub 1 over 1 minus r. Here, they're just referring to that as s. If the series will diverge if the absolute value of r is greater than or equal to 1. So if you have a geometric series and the common ratio is greater than or equal to 1, it's going to diverge. All right, let's look at example 3 and see what we can figure out. If they say, determine whether the series is convergent or divergent. If it's convergent, find its sum. All right, so we've got this series right here. It's got an n in it, but it doesn't have it everywhere. Let's see what we can do with this. We can rewrite this as the sum from n is 1 to infinity of 4 over 1 times 1 over 5 to the n, because when you multiply fractions, you multiply straight across. And then you can say, well, this is really the sum from n is 1 to infinity of 4 times 1 to the n over 5 to the n, if you want to think of it that way, because 1 to the whatever is still 1. So we can think of this as 4 times 1 over 5 to the n. And in that way, we have found this to be a geometric series, which is great. So we can say, well, this is our geometric series. So the common ratio here, where r is 1/5. And so we can say, well, the absolute value of r is the absolute value of 1/5, which is less than 1. So this is going to converge. We know it's going to converge. Now, what is it going to converge to? What is its sum? Well, the sum is the first term, a sub 1 over 1 minus r. So the first term is where you let n be 1, or whatever this first index is. Notice in B, n doesn't start as 1. They don't always start at 1. So you start with whatever they tell you to start at. That's what I mean by the first term. So here they say start at 1. So this is going to be 4 over 5 to the 1, or 4/5. That's the first term. That's a sub 1 up here. So the sum is going to equal to the first term divided by 1 minus the common ratio. And the common ratio is 1/5. All right? So we get 4 over 5 divided by 1 minus 1/5 is 4/5. So we get 4/5 divided by 4/5. This will converge to 1. That's the sum of that one. That's part A. All right, let's look at B. Notice that all series do not have to start at 1. They can start at 0. They might start at 2 or 3 or something like that. But this one happens to start at 0. That's okay. We accept that. Okay, but this is what we're adding up. What is this mess? Well, let's look at this. Let's see. This is the sum from n is 0 to infinity of 3 to the n plus 1 is the same thing as 3 to the 1 times 3 to the n. If you recall your exponent rules, when you have like bases raised to powers and they're being multiplied, the powers will add. So we can think of that as 3 times 3 to the n over 4 to the n. And then we can think of this as n to 0 to infinity of 3 to the 1 times 3 to the n over 4 to the n, which is n is 0 to infinity of 3 times 3 over 4 to the nth power. That's what we have right there. Okay, and we can spot this. Okay, this is another common ratio. And what is the common ratio r? In this case, r is equal to 3 over 4. All right, so this common ratio is, the absolute value of it is less than 1. So this will also, it's going to converge. This series will converge. Okay, what will it converge to? Well, we have this nice little formula. It will converge to the first term divided by 1 minus the common ratio. Okay, the first term, even though n doesn't start at 1, the first term is when n is 0. So that's fine. The first term is going to be 3 to the 0 plus 1 over 4 to the 0. That's the first term over 1 minus the common ratio of 3/4. All right, 0 plus 1 is 1. So that's 3. 4 to the 0 is 1. So that's 3 over 1 over 1 minus 3/4, which is 1/4. So basically we have 3 over 1 times 4 over 1, a fraction divided by a fraction, and so it's going to converge to the number 12. Okay, I'm going to break this into 2 videos. This is part 1 of the series video.